Welcome back to the deep dive. Today we are going to look at something that I actually like to call industrial magic.
Industrial magic.
Yeah.
That is well, it's a very romantic way to describe what I usually just call physics, but I do like where your head is at.
Yeah.
What exactly makes it magic?
Well, think about it. If you walk into a massive refinery or, a paper mill, it looks like absolute chaos.
Oh, totally.
You've got these huge cranes hoisting massive slabs of rock. You have fluids rushing through pipes at terrifying speeds, valves snapping shut faster than you can even blink.
Right.
It's loud, it's hot, and to the untrained eye, it just looks completely unpredictable.
But it's not unpredictable. It's actually, I'd argue, it's the most predictable thing on Earth, if you just know the rules.
Exactly. And that is the magic trick. It's all this raw, chaotic force being wrestled into something useful. Oil, paper, electricity.
Yeah.
And the materials we're breaking down for you today, they argue that all of that complexity, all that noise, really just boils down to controlling a single currency.
Yeah.
Energy. And just to be perfectly clear for everyone listening, we are not talking about the energy you feel after a double espresso
Right.
or the vibe of a room. We are unpacking the literal nuts and bolts of how the physical universe pays for motion.
It really is the accountant's view of the universe.
Hmm.
The source material we have today is this comprehensive technical training module, and it starts with a definition that is, honestly, deceptively simple. It defines energy as the capacity to do work.
The capacity to do work. Now, I want to unpack this immediately because work is one of those words that means one thing in the office and something totally different in a factory.
It really does. I mean, in your daily life, work might mean sitting in a Zoom meeting or answering a bunch of emails. But in physics, strictly speaking, that doesn't count.
Which is tragic because it definitely feels like work.
It is tragic. But in the physical sense, work capital W has a very rigid definition. Work equals force applied over a distance. W equals F times D.
Okay, so let's use the classic example to make this concrete for you. If I go outside and push against a brick wall for 3 hours, and I'm sweating, my muscles are shaking, and I'm just totally exhausted, have I done any work?
In the eyes of physics, you have done exactly zero work.
That is just harsh.
It's just the math. The distance, D, is 0. If the wall didn't move, you didn't do work on the wall. You certainly expended biological energy. I mean, you burned calories, you generated heat,
Right.
but you didn't transfer that energy into the system of the wall.
Okay, but what if I apply that same exact force to a lever, and I manage to move a heavy crate, say, 1 meter?
Now you're in business.
Yeah.
You applied force, and movement happened. You have performed work. You have successfully transferred energy from your body into the crate.
So it's a transaction. That's why I really like the currency analogy here.
That is the perfect way to view it. Think of work as the act of spending. You spend work to gain energy. Or, conversely, a machine spends its energy to do work. It's a direct exchange rate.
And our mission for this deep dive is to decode that exchange rate for you. We're going to look at the 3 main bank accounts where this energy gets stored once you've done the work.
Right. We have kinetic energy. We have the energy of motion. We have gravitational potential energy, which is banking energy by lifting things up. And we have elastic potential energy, which is storing energy in things like springs.
And to make this real, so it's not just abstract math on a chalkboard, we're going to walk you through the specific industrial case studies from the documentation. We've got speeding carts, massive rocks suspended over rivers, and some incredibly dangerous springs.
Let's start with the speed, the kinetic energy account.
The thrill ride. So the scenario here involves a mass of roughly 6 kilograms. It's 5,980 grams to be exact in the source. Imagine a heavy metal block or a cart just sitting at rest.
Okay.
Then a machine applies force, so it does work on the cart, and accelerates it to 155 kilometers per hour.
Which is fast. That isn't a gentle nudge. That is significantly faster than highway speeds.
Right, so the question is how much energy is now locked inside that moving cart?
This brings us to the very first hurdle of industrial physics, the units. The data gives us grams and kilometers per hour. If you try to plug those numbers directly into an engineering equation, your bridge is going to fall down.
You have to speak the language of the joule.
Exactly. The joule is our universal unit of energy. To get joules, we need kilograms and meters per second. So we have to tidy up the data first. We treat the mass as roughly 5.98 kilograms.
Because there's 1,000 grams in a kilogram.
Right. And that 135 kilometers per hour, we have to strip that down to meters per second.
The conversion is pretty standard. You divide by 3,600 seconds for the hour, Multiply by 1,000 meters for the kilometer.
Yeah, but the result is what really matters. 155 kilometers per hour translates to roughly 43 meters per second.
Think about that for a second. 43 meters, that's nearly half a football field. Covering that entire distance in a single snap of your fingers, that is significant velocity.
It is. So we have the mass, we have the velocity. Now we need the formula for the kinetic bank account.
The classic equation. E sub k equals 1/2 mv squared. 1/2 times mass times velocity squared.
There is a tiny number in that formula that I think is the single most important thing for anyone dealing with safety to understand. The squared.
The squared, it changes everything.
It changes everything. It means the relationship isn't linear. If you double your speed, you don't just double your energy, you quadruple it.
Which is exactly why car accidents at 80 miles an hour are so much more catastrophic than accidents at 40.
Exactly. It's exponential growth. You are packing 4 times the destructive power into the vehicle. In our case study, when we take that 43 meters per second, square it, and multiply by the mass and the half, we end up with a kinetic energy of approximately 5.54 kilojoules.
5.54 kilojoules. Just to ground us, what does that number represent in terms of our work currency?
Well, go back to the work definition. Remember, work puts money in the bank. That means the machine that pushed this cart had to perform exactly 5.54 kilojoules of work to get it to that speed.
It paid for it.
Yes, it's the work energy theorem. The machine paid 5.54 in work, and the cart banked 5.54 in kinetic energy.
In a perfect world, anyway.
Right, assuming we ignore friction for a moment. But the balance sheet has to balance. The energy didn't just appear out of thin air, it was paid for by the machine.
You know, there's a note here in the material about energy being scalar versus vector.
No.
That feels like a distinction that matters more to engineers than to me, but walk me through it. Why does the text make such a point of saying energy is scalar?
It actually matters a lot conceptually. Velocity is a vector. It has direction. Driving north at 100 miles per hour is physically very different from driving south. You end up in a totally different place. But energy is scalar. It has magnitude, but no direction.
So the cart has 5.54 kilojoules of energy, regardless of whether it's headed left, right, up, down, or straight at my face.
Exactly. It's just the amount of oomph the object has. It doesn't care about the compass. 30 joules is 30 joules. It's essentially a quantity of potential chaos.
I really like oomph as a technical term. Let's stick with that. So that's the energy of movement. But flight series aren't just things moving around. A lot of time, energy is sitting completely still, just waiting. Which leads us to the second bank account, gravitational potential energy.
This is the shift from the energy of motion to the energy of position. This concept is vital for cranes, elevators, hydroelectric dams, basically anything that lifts mass against gravity.
The case study they use here is a 40-kilogram mass, so a decent-sized crate, and we are lifting it 923 centimeters into the air.
I see you pausing on that number.
I am. 923 centimeters. Because I know the rule now. We don't do centimeters in the land of joules.
We do not. We need meters, so call it 9.23 meters.
Okay, almost 10 meters up, roughly 3 stories high. We've done the work to lift it, now just hang in there. How do we calculate what's in this specific bank account?
The formula changes. For kinetic, we cared about speed, V. For potential, we care about height. The formula is E sub P equals mgh, mass times gravity times height.
And gravity is the silent partner here.
Always. Little g is the acceleration due to gravity. On Earth, that's a constant 9.81 meters per second squared. It's the invisible tether pulling everything down. When you lift that crate, you are actively fighting that 9.81 every single inch of the way.
So we multiply the 40-kilogram crate by the 9.81 pull of Earth by the 9.23 meters we lifted it.
And the calculation comes out to approximately 3.62 kilojoules.
Now, visually, this is kind of weird to think about. The cart was zooming at 155 kilometers per hour. It was screaming down the track. I easily get that it has energy. But this crate is just hanging there. It's dead still.
Yep.
But you're saying it currently has 3.62 kilojoules of energy ready to go.
Think of it like a battery. A battery sits on a shelf and does absolutely nothing, but it's full of chemical potential. This crate is full of gravitational potential. You charged it up by doing the work of lifting it. The energy didn't disappear. It's literally stored in the position itself.
It's an investment account. You put the work in, and it sits there until you make a withdrawal.
And if you cut the cable...
Make a very rapid withdrawal.
Exactly.
Which we'll get to in a minute with the falling rock scenario, which is a fantastic visualization. But before we drop anything, there is one more type of potential energy we need to cover. And this one honestly feels the most industrial to me. It's not about height, and it's not about speed. It's about stress.
Elastic potential energy. The energy of springs.
Now, when I say springs, my mind goes to a ballpoint pen or maybe a mattress, but the example in the notes is a control valve actuator. I actually had to look up figure 3 to really visualize this. It's a device that uses air pressure to open and close huge valves.
Correct. In a refinery, you have thousands of these things. Air pushes a metal stem down to close the valve, and in doing so, it compresses this big, heavy industrial spring. When you release the air, the spring snaps the valve back open. It's a fail-safe safety mechanism. If the power fails, the spring takes over and forces the valve to a safe state.
And the physics of that snap is governed by Hooke's law.
F equals kx, a beautiful, simple little equation.
Let's break it down for everyone. X is the distance the spring moves. That's simple enough. But kk is sort of the personality of the spring.
That's a good way to put it. K is the spring constant, or the stiffness. It tells you exactly how hard the spring fights back. A slinky has a pathetic K. The suspension on a mining dump truck has a massive K. It represents how many newtons of force you need to compress it by exactly 1 meter.
And looking at the specs for this valve spring, it is definitely no slinky. The spring rate is listed as 830 pounds force per inch.
Which in imperial units, so we have to do a massive conversion to get back to our metric standard for joules. When you crunch those numbers, the spring constant comes out to roughly 145,348 newtons per meter.
145,000 newtons per meter. Can we just pause on that? That sounds incredibly stiff.
It's immensely stiff. To squash this specific spring down by 1 meter, you'd need a force equivalent to stacking about 15 small cars on top of it.
But in the valve, it doesn't move a meter.
No, thankfully. The stroke, which is the compression distance x, is listed as 0.4375 inches. That's tiny. It's about 11 millimeters.
So we have this monster spring, but we're only annoying it a little bit. We're only squishing it 11 millimeters. How much energy is actually stored there?
Well, the formula for elastic potential is E sub p equals 1/2 kx squared.
Which looks exactly like the kinetic energy formula. 1/2, a constant, and a variable squared.
Nature really likes its patterns. When we plug in that massive stiffness k and that tiny distance x squared, the result is surprisingly small.
Yeah.
It comes out to only about 8.97 joules.
Wait, 9 joules.
Yeah.
The kinetic cart had over 5,000 joules. The lifted box had over 3,000. This industrial death spring only has 9.
It seems wrong, doesn't it? But it's all about the distance. Remember, work is force times distance. You have a huge force, but the distance is almost microscopic, just 11 millimeters. So the total energy banked is actually very low.
That is so counterintuitive. I'd be terrified to put my finger in that spring.
Well, you absolutely should be. Please do not put your finger in the spring. The energy is low, but the force is high. The calculation shows the force required just to hold it compressed is about 1.62 kilonewtons.
Wow.
That's like balancing a motorcycle on your thumb. It will crush you, but it won't explode the building.
High force, low energy. That's a distinction that probably saves a lot of confusion in engineering meetings. It's the difference between being crushed and being blown apart.
Precisely. You can have immense pressure without immense energy storage, provided nothing is moving very far.
Okay, so we've got our 3 key players. The speeding cart for kinetic, the lifted crate for gravitational, and the compressed spring for elastic. Now, the text brings this all together in a really dramatic way. It's the centerpiece story of the module.
The Law of Conservation of Energy, starring The Falling Rock.
This feels like a scene from an action movie. We have a 1,000 kilogram rock that's a full metric ton suspended by a crane. It is hanging 100 meters directly above a river.
And because this is a physics thought experiment, we are in an idealized world. No air resistance, no wind, just pure mathematical forces.
Scene 1. The rock is at the top, 100 meters up. It's not moving. What's the energy situation?
Well, velocity is 0, so the kinetic account is totally empty. But height is 100 meters, so we calculate the gravitational potential. Mass, 1,000 times gravity, 9.81 times height, 100. That gives us 981,000 joules, or 981 kilojoules.
So the total energy of the system is 981 kilojoules. That is the budget. That is everything we have to play with.
And the law of conservation is strict. Energy cannot be created or destroyed. It can only transform. That 981 kilojoules is locked in. It cannot leave the system.
Scene 2. The crane operator hits the button. The clamp opens. The rock drops.
Immediately, things change. Height starts decreasing. The rock is falling toward the river. That means the potential energy count is rapidly draining. Every single centimeter it falls, it loses potential energy.
But the money has to go somewhere. The account can't just evaporate.
It goes into the kinetic account. The rock speeds up. Potential turns directly into speed.
The text actually freezes the frame at the halfway point. The rock is exactly 50 meters above the water. It's in free fall.
Logic tells us if we are at half the height, we should have half the potential energy left. And the math backs that up perfectly. MGH at 50 meters gives us 491 kilojoules.
Exactly half of 981. So we've lost 491 kilojoules of potential energy. Where is it?
It is now kinetic energy. The rock is hurtling downwards. If you do the math on the velocity required to hold 491 kilojoules of energy, you find the rock is falling at roughly 31.3 meters per second.
So it didn't gain energy from nowhere, it just cashed in its height for speed.
It's a pure currency exchange. You're trading altitude for velocity.
Scene 3. The impact. The rock hits the surface of the river. Height is 0.
At height 0, the potential bank account is closed. Balance, $0.
Which means the kinetic account must be holding the full amount.
Exactly. All 981 kilojoules are now kinetic energy. We have fully converted position into motion.
And how fast is a 1-ton rock moving when it has 981 kilojoules of kinetic energy?
We run the numbers, solving for V, and it comes out to roughly 44.3 meters per second. That's nearly 160 kilometers per hour.
Imagine a small car made of solid rock hitting the water at 160 kilometers per hour.
The splash would be significant.
But the beauty of it is the balance. 981 at the top, 981 in the middle, 981 at the bottom. The universe balanced the books perfectly.
It creates a predictability that engineers rely on every single day. This is how we design roller coasters.
Yeah.
If you know the height of the first hill, you know exactly how fast the car will be going at the very bottom. Before you even weld the first piece of track, you just look at the height. You don't need to guess.
The notes give us one more example of this, just to prove it works on small scales too. A pendulum.
Yes. A 4-kilogram bob on a short half-meter cord, same exact logic. You pull it up to the side, so you're lifting it. You store potential energy.
Yeah.
The text says you do about 19.6 joules of work to lift it to that horizontal position.
Then you let go. It swings down.
As it swings, potential turns to kinetic. At the very bottom of the arc, the height is 0 relative to the pivot. Potential is 0. Kinetic is maximized.
And the speed at that bottom point.
About 3.13 meters per second.
It's the rock problem, just in a grandfather clock.
Physics doesn't care about size. The rules for the crane are the rules for the clock. Conservation is universal.
So we've unpacked the currency of motion. We've seen how work puts money in the bank. We've seen the 3 main accounts. And we've seen that you can transfer funds between them smoothly, but you can't fake the total.
That is the core takeaway. In any industrial process, energy is just shifting forms. We burn gas to boil steam, that's chemical to thermal. The steam pushes a turbine, thermal to kinetic. The turbine spins a generator, kinetic to electrical. It's all just transformation.
Now I want to leave you, our listeners, with one final thought. The text ends with a very brief mention of a bullet. It's almost a throwaway line in the source, but I think it's the most provocative part.
Ah, yes. The bullet penetrating a block of wood.
Think about the conservation law we just discussed. A bullet is flying, it has massive kinetic energy, it hits a block of wood and buries itself deep inside. And then it stops.
Velocity becomes 0.
Right, so kinetic energy goes to 0, but the bullet didn't go up in the air, so it has no gravitational potential. It's not a spring, so there's no elastic potential. The energy just vanished.
But we just spent 15 minutes saying energy can't be destroyed.
Exactly. So where did it go? We had a massive amount of joules, and suddenly the bullet is stopped dead. The books don't seem to balance at all.
This is the question that opens the door to the next level of physics. Thermodynamics. We assumed frictionless environments for the rock and the cart to make the math pretty and clean. But the bullet is the real world. That energy didn't disappear. It became heat. Intense heat. If you touched that bullet right after it stopped, it would burn you severely. The wood fibers around it would literally be charred. The energy also became sound, the crack of the impact, that's acoustic energy radiating away, and it went into deformation, shattering the wood structure.
So it didn't vanish, it just turned into a mess.
It turned into chaos.
Yeah.
Entropy. The energy's still there in the universe, but good luck trying to turn that heat and splintered wood back into a speeding bullet.
That's a really humbling thought. You can turn height into speed easily, but once you turn speed into heat, it's really hard to get a refund.
The universe charges a steep fee for that transaction. It's what we casually call losses in engineering, but really, it's just energy taking a form we can't use anymore.
Something to think about the next time you hit the brakes on your car and wonder where all your speed went. It's just warming up your tires. Thanks for joining us on this deep dive into energy. We'll see you next time.